Good morning, students. Today I'm going to cover a new topic, that is multi-degree freedom vibration system by using STODOLA'S method. We have already dealt with Rayleigh's and Dunkerley's method. Now this is the third method for calculating the fundamental natural frequency of multi-degree freedom vibration system. So what we are going to do in this is that we will discuss about the principle of STODOLA'S method, and then we will explain STODOLA'S method step by step by using example problem. So STODOLA'S method is an iterative method with the characteristic that it converges very fast to the final solution. So if there is n degree of freedom vibration system, then we need to calculate the lowest frequency of the vibration system. So this method proves to be useful in terms of calculating the lowest frequency or the fundamental frequency of this vibration system. So we have to iterate over trials, number of trials, and we would come down to the final answer for the natural frequency of the vibration system. So let us come down to directly to the method, step-by-step method of this method. So the first thing which, if we want to calculate the fundamental frequency using STODOLA'S method, first thing which we need to do is that we need to assume the deflection curve. Means that we have to start the problem by assuming the deflection under different masses. I can explain this through this example using the whiteboard. So here, let me start doing it on. So suppose there is a string and this string is connected with number of masses onto it, say mass 1, mass 2, mass 3, okay, and since this mass 1, mass 2, mass 1, mass 2 and mass 3, they are going to deflect under these masses. Say this is the deflection here, that deflection I assume to be x3. Similarly, the deflection here, if I assume this deflection to be x2, and similarly the deflection here, if I assume this deflection to be x1, then what I have to do is that I have to start the problem by assuming the value of x1, x2 and x3, assuming that initial start value are taken to be very simple values as 1, 1, 1 for all the 3 deflections which we are obtaining here. Okay, so the first step in this method is to start with by assuming some deflection curve. Okay, so deflection curve we start with the some assumed value of deflection under different masses. Now, with these deflection values, you need to calculate the different forces, dynamic forces coming on different masses. So if suppose x1 is the deflection under mass m1, so the dynamic force for mass 1 would be m1 omega 1 square and x1 in place of y. Y is the deflection of mass 1, so it is called as m omega 1 square x1. Okay. Similarly, F2 would be the dynamic force acting at, or inertia force acting at point 2, that would be given as F2 is equal to m2 omega 1 square, since I am assuming that all the masses are vibrating with the same natural frequency. So it would be m2 omega 1 square, and in place of r or y, I'll put the value of x2. Okay. So similarly, you can calculate all the inertial forces which are acting on different masses. I can explain this through, again, coming to the whiteboard. So once I have assumed these deflection, what I will do is that I'll calculate the first inertial force here, that is F1 would be given as M1 is the mass acting, omega is the natural frequency I'm assuming constant for all three masses, since this string is moving with the same natural frequency. So I'll represent this as omega 1 square, and x1 is the deflection under the mass m1, so the inertial force acting here would be f1. Similarly, I'll calculate the inertial force which is acting under mass 2. For mass 2 would be m2 omega, since mass 2 is also moving with the natural frequency omega 1, so omega 1 square multiplied by x2. Similarly, you will calculate the value of f3. Okay. So after first step, in the second step, you need to calculate all the inertial forces which are acting. Okay. So this is the first step where you are calculating, or where you are assuming initial deflection, and in the second step, corresponding to those deflection, you're calculating the inertial forces. Okay. Then in the next step, what you need to do is, that find the new deflection curve using inertial loads. Okay. So once you have calculated these inertial forces, you need to calculate what are the new deflection curves because of these inertial forces. Because initially we assumed some deflection values, but now we have to calculate the new values of deflection because of these inertial forces. Okay. So I'll go back again on the whiteboard and we'll try to explain this, the step number 3. So here what I am going to do is that I am going to take another example. Say there is a 2 degree of freedom vibration system where masses are connected with the two strings, say this and this masses m2, and sorry for my writing, and this is m1. The spring stiffness here is taken to be K, and again here the spring stiffness is taken K. Okay. So what is to be done is that for calculating the new deflection because of these inertial forces, what we need to do is that we need to first of all calculate that what are the different deflection because of the unit force applied at single masses. Okay. So what I will do is that I'll calculate, suppose I apply a unit force here on mass 1. Okay, unit force. So this force, unit force which is applied at mass 1 would cause a deflection in the mass 1, okay, and this would also cause deflection in the mass 2. This deflection is called as delta 2-1 because this is the deflection because of the force applied, unit force applied at point 1. So this is deflection at point 2 because of the unit force applied at point 1. Similarly, this would be the deflection at point 1 because of the unit force applied at point 1. Okay. Now I need to calculate the value of delta 1-1 and the value of delta 2-2. Okay, 2-1. Similarly, what I will do in the next instance, I would calculate the deflections when, again, I'll take the same, it will take some time to redraw it, but I'll draw it again. Suppose this is the spring. Sorry for my writing again. And these are the two masses. Now, suppose now I apply the unit force at mass 2. Okay, so this unit force which is applied at mass 2 would cause some deflection at mass 1. So I'll call that deflection at point 1 because of unit force applied at point 2. Similarly, it would cause deflection at point 2 because of the unit force applied at point 2. So this would be delta 2, 2. Okay. Now, how to calculate the value of delta 1-1? How to calculate the value of delta 1-1 and delta 2-2? We need to calculate the value of delta 1-1 and we need to calculate the value of delta 2-1. Similarly, we need to calculate the value of delta 1-2 and delta 2-2. So that those values have to be calculated by drawing the free body diagram. I can explain it here. For example, if you want to draw the free body diagram of this mass 1, okay, and mass 2. So in this case, I'll draw this mass 1 here, okay. Now this mass, there is a unit force which is applied here, is in this direction. So I'll mark this as unit force. Now you know that this mass is moving in this direction. This mass is moving in this direction. So this would cause extension of this spring. And how much would be the extension of this spring? That would be by an amount delta 1-1. So this spring is going to exert a force onto this mass in this direction, and this force is going to be K times of delta 1-1. Okay. Now take example of this spring. This spring is subjected to two deflections, one because of the second mass, that is delta 2-1, and another deflection is delta 1-1. So if I assume that delta 1-1 is more than delta 2-1, so that would result into compression of this spring. There would be a compression of this spring if I assume delta 1-1 is more than delta 2-1. So if it is a compression, then this spring would cause a force on this mass 1 that is equal to K multiplied by the relative displacement, that is delta 1-1 minus delta 2-1. Okay. So balancing the forces on mass 1, I take positive direction as this one. I take positive direction of the force as this one. Okay. So I can write this as 1, since all the other spring forces are acting in negative direction. So I can write this as K delta 11 minus K delta 11 minus delta 12, okay, is equal to 0. So through this equation, I would like to find out the values of delta 11 and delta 12. Since there are two unknowns, so you can find out the value of delta 11 in terms of delta 12. Now you need to draw the free body diagram for mass 2 from here. Free body diagram of mass 2. I draw it here. So I take the mass 2. I take the mass 2, and here you would find that it is connected with only one spring, and the force, since it is under compression, so this spring would cause a force on this mass that is equal to in this direction, and the value is same as delta 11 minus delta 12. Okay, so there is only one force acting onto this, and there is no other force acting on this mass in the first case. So balancing the equation, I would say that K delta 11 minus delta 12 is equal to 0. So this is going to be 0. So from here, I would calculate the value of delta 11 in terms of delta 12. Okay, and there I'll put the value of delta 11 and delta 12 here, and I can calculate the value of delta 11. Okay, so this is how you would calculate the value of all deflections because of the inertial forces. Mind here that, remember that these deflections are because of unit load. So when I apply an inertial load, then the total deflection at these points would be force multiplied by this deflection. Okay, because this is the deflection because of the unit load, so the total deflection when the inertial forces are applied, then this would be multiplied by the force applied there. Okay, so if I want to find out that what is the total deflection at point 1, you would appreciate the total deflection at point 1 would be because of the unit load applied at point 1, and total deflection at point 1 would be because of the unit load applied at point 2. So I would say that it is sum of unit load applied at point 1 and sum of unit load applied at point 2. So these are the deflection at point 1 because of the load applied at point 1, and deflection at point 1 because of the load applied at point 2. Since these deflections are because of unit load, so in order to calculate the total deflection, I need to multiply it by F1. So this would give you the total deflection because of the inertial force applied at point 1, and here it would be given as total deflection at point 1 because of the inertial force applied at point 2. So this is going to give you the new deflection at point 1. Okay. Similarly, if I want to calculate the new deflection at point 2, then this would be given as unit deflection at point 2 because of unit load applied at point 1, and then deflection at point 2 because of unit load applied at point 2. Since the force applied at point 1 is not unit, it is inertial force, so I multiplied by F1, and since force applied at point 2 is not unit, it is this much of load, so I'll multiply it by F2. So I will calculate the value of new deflection. Okay. So what we are going to do is that we started with initial values of uh, deflection, assuming initial values of deflection, then calculating the inertial forces because of the assumed value of deflection, and finally we come out with the new values of deflection. Now what we will do is that this is step number 1, this is step number 2, this is step number 3. Now what we are going to do is that we are going to match these values with the assumed values. Now we have to match these values with the assumed values. Okay, if they are not matching, then what we are going to do is that we will start a new iteration by assuming these new values as the initial values. Okay, and if they are matching, if these values are matching, then what we will do is that we can calculate the value of omega square by just equating them. Okay, so if these values are not matching, then what we'll do is that we'll have to start with a new new iteration by assuming the new values of the assumed deflection curve as the calculated values. Okay, and then same steps, then again we will have to find out the inertial forces with the new values of deflection, and then we will have to calculate again the new values x2 double dash. Okay, now we'll again match these values with the previous one. So if these are matching, then we'll equate and calculate the value of omega square. If they are not matching, then what we'll do is that we'll start with these values as the assumed values. Okay, and these values as an assumed values, and then we'll calculate the inertial forces because of the new values, and then we'll calculate next new values here. Okay, and then again start matching. So this iteration keeps on going until there is a match between the calculated values and the assumed values of deflection. Okay, and once we get the matching of the calculated value and assumed values, then by equating them, we can calculate the fundamental frequency of the n-degree vibration system. Okay, so I'm going back to the slide. So I've explained you the method of STODOLA'S method. This is how we have to go along with this. Okay, so let me explain this through an example. So this is a 3-degree vibration system. It's connected with spring of KKK. I do not know whether it is K or no, this is not K, this is 3K. So this value has to be taken as 3K, K and K, and this value is to be taken as 4M. This value is taken as this value is to be taken as 2M, and this value has to be taken as M. Okay, so what we'll have to do, the first step, in the first step, let us calculate delta 11, delta 21, delta 31. Similarly, if I apply the unit load at point 2, so here the load deflection would be delta 1, 2, and so on and so forth. So first of all, I would calculate the deflections because of the unit loads applied at different places. Okay, so let me go back, and using the whiteboard, I'll use the new board. Okay, so I'll clear. Okay, so let me start with the problem which we have taken here. So this is first mass which is acting here. This is second mass, and this is third mass, which is a 3-degree vibration system. Okay, this is 4m. Okay, this is 2m, 2m. This is m. This is 3k. This is k, and this is k. So what I will do is that first of all, I would calculate what are the deflections because of the unit force applied, so that later I can use them in order to calculate the new values of deflections. So first of all, I would try to apply, I'll now simply draw it, uh, I'll try to draw it very fast. So what I will do is that I'll so this now initially I apply the unit load on mass 1. This would cause deflection here. Okay, this would also cause deflection here. This would also cause deflection here. So deflection here would be delta 1 because of the load applied at point 1. Here the deflection at point 2 because of the load applied at point 1. Here deflection at point 3 because of the load applied at point 1. Okay. Similarly, I will go with another applying unit load here at the second mass. Okay, so if I apply unit load here on the second mass, unit load, so this would cause deflection here. This deflection would be delta 1, deflection at point 1 because of the unit load applied at point 2. This deflection would be deflection at point 2 because of the unit load applied at point 2, and this would be the deflection at point 3 because of the load applied at point 2. Similarly, the third case where I would apply and I would apply, so unit load is applied here now in this case. So this would cause deflection here. And can you guess what would be the value of this reflection? Because deflection at point 1, because of the load applied at point 3. This is deflection at point 2 because of the load applied at point 3, and deflection at point 3 because of the load applied at point 3. Okay, so you need to calculate the value of delta 11, delta 21, delta 31, delta 12, delta 22, delta 32, delta 13, delta 23, and delta 33. Okay, and how do you calculate? I just explained you this through by drawing the free body diagram. So I can explain this for first example, and you have to repeat this in the same way so that you can calculate the values for others as well. So here, if you apply a unit load on mass 1, see, this is a 3K spring. This is a stiffness of this spring is 3K. So this would cause extension in the spring. This would cause extension in the spring because this mass is moving in this direction. Okay, this mass is moving in positive x direction. So that would extend, and this spring would cause a force in the opposite direction on the mass. So if I draw the free body diagram of mass 1, so
there would be a force because of the spring 1 on this would be 3K is the stiffness multiplied by deflection of the spring, that is delta 1 1. Okay, and you know that there is a unit force applied on this mass is this. Now take the example of the second spring. The second spring having stiffness K. Now since I am assuming that delta 1 1 is greater than delta 2 1. Okay, so if delta 1 1 is more than delta 2 1, so this spring gets compressed. There is a compression of the spring. And how much is the compression of the spring? Delta 1 1 minus delta 2 1. So this spring compression would then exert a force onto this mass that would be equal to K times of delta 1 1 deflection minus delta 2 1. Okay, now take the mass 2. It is connected with the 2 spring. So the spring here, which is, this spring is exerting force on this mass in this negative x direction. So it would also exert opposite force on this mass. So I can simply say that this is mass 2. Now this force would be equal and opposite because spring is same between them. Okay, so this is mass 2, this is mass 1, 4m. Okay, now there is a spring between these two masses. So assuming that delta 2 1 is greater than delta 3 1, then this force, again, this spring would undergo compression since this deflection is more than this deflection. So compression would be delta 2 1 minus delta 3 1. So it is going to exert a force here on this, that is K times of delta 2 1 minus delta 3 1. Okay. Similarly, if I draw for the third mass connected with only one spring. This is third mass, which is connected with only one spring, and the force coming would be opposite to, because for every action there is an equal and opposite reaction. So there would be opposite force and the value of the force is same. So you have calculated, drawn the free body diagram for case 1 where unit load is applied at point 1. Now balancing these equations on different masses of forces, then you can get the values of delta 2 1, delta 3 1, and so on. For example, I take for mass 3 and I write the equilibrium equation. So there is only one force acting on this mass, that is this one. This is the only force which is acting. So I can say that K times of delta 2 1 minus delta 3 1 is equal to 0. So from here, I can calculate delta 2 1 is equal to delta 3 1. Okay. Similarly, I would apply the equation of equilibrium equation for mass 2. There are only two forces acting. So this direction is taken, positive x direction of the force is taken as positive, and negative x direction of the force is taken negative. So this force minus this force is equal to 0. So we'll get the other values of delta 1 1 or delta 2 1. Similarly, we'll apply or balance the equilibrium equation for the third mass. So in this way, we will be able to get the values of different deflections. Then we will do the same procedure for the second case, and then we will do the same procedure for the third case. So we will calculate the values of unit deflections. Now, one more thing here is that this is the unit deflection at point 1 because of the load applied at point 1. This is the unit deflection again at point 1 because of the load applied at point 2. And this is also the unit deflection, deflection at point 1 because of the unit load applied at point 3. So the deflection, if I want to calculate deflection at point 1, new deflection, because I assumed initial deflection as 1. Initial deflection, in step 1, I have assumed initial deflection at mass 1 is equal to 1. But you have to calculate the new deflection after applying the initial forces. So this would be summation of deflection at different loads and at point 1, delta 1, 3. And these deflections are because of the unit load applied at different masses. So if I apply force F1 here, then this would be F1 delta 1, 1. And if I apply the force, initial force at point 2 is F2, and inertial force at point 3 is F3, then the new deflection at point 1 dash would be given by this formula. Hope you might have understood this. So let me go back to the, so in this way, I apply unit load and I have calculated the values of all the deflections because of the unit load applied at point 1. So in this case, delta 1, 1 comes out to be 1 by 3K. And then I'll apply the unit load at mass 2 and draw the free body diagram and write down the equations and solve them, those equations. Then I'll apply the unit load at mass 3 and then draw the free body diagram and write down the equations, equilibrium equations, and solve for the deflections. So the deflection values, all 6 values of deflections are calculated like this.
Now let us start with the STODOLA'S method. So first of all, you need to calculate all those deflections at different masses because of the unit load applied at different masses. Okay. Now, as I have told you that in STODOLA'S method, you have to start with an initial displacement, assumed initial displacement. So in this case, we assumed as x1 is equal to 1, x2 is equal to 1, and x3 is equal to 1. They are in the ratio of 1, 1, 1. Now, because of these inertial forces, these assumed deflections, we will calculate the value of inertial forces at different masses. So the first mass is applied, first mass is equal to 4m. So the inertial force at first mass would be 4m multiplied by omega. Omega is common for all masses, multiplied by the initial deflection which we assume. So this comes out to be 4m omega square. And inertial force at mass 2 would be the mass, that is 2m multiplied by omega square into x2. x2 is 1. So this comes out 2m omega square. And inertial force at point 3 would be, or the mass 3 would be equal to mass multiplied by the common natural frequency omega square multiplied by x3. x3 value is assumed to be 1. So this comes out to be m omega square. So we have done second step, calculating the inertial forces based on the assumed deflection. Now we have to calculate the new deflections because of the inertial forces. So as I told in the last slide through whiteboard, I have told you that the new deflections at point 1 would be calculated as F1 delta 1 1 plus F2 delta 1 2 plus F3 delta 1 3. Similarly, X2 dash would be calculated by multiplication and summation of these values, and X3 would be calculated like this. Now we have all those values already calculated, F1 delta 1 1. So we'll put all those values and calculate the new values of deflections, x1 dash, x2 dash, and x3 dash. Now, once these values are calculated, we take the ratio of these values. They come in the ratio of 1 raised to 2.3 raised to 2.7. So once you have calculated the ratio of the new deflections, you have to match whether the new deflections are same as the assumed deflections. So assumed deflections were 1 raised to 1 raised to 1, whereas new deflections comes out to be
1 raised to 2.3 raised to 2.7. Okay, remember that these new deflections are calculated based on the inertial forces. Okay, so these values of new deflections are not matching. So what we need to do is that we have to go back and repeat the process again. But now in the next iteration, what we'll have to do is that we start with the assumed deflection as 1 raised to 2.3 raised to 2.7. So x1 value is taken, x1, the new values of x1 dash is taken as 1, x2 dash is taken 2.3, and x3 dash is taken as 2.7. Okay. So we start with the new iteration, let me try with the calculated value of new deflection as the initial values of assumed deflection. Now again, based on these deflection values, we calculate the inertial forces. So inertial forces for these assumed values, so mass, that is first mass is 4m omega square into x1 dash. So x1 dash is 1. Similarly, f2 dash would be mass 2m omega square into x2 dash. x2 dash here is 2.3. So this value comes out 4.6 m omega square. Similarly, f3 dash mass into omega square into x3 dash, that is 2.7. So this comes out to be 2.7 m omega square. Now, once you have calculated these initial values, inertial forces, now you have to calculate again in the next step, new values of deflections by taking into account the deflections which we have already calculated at different points. So the same formula to be used, putting the values of new values of inertial forces here, you will get the values of new values of deflections. Now these new values of deflection, x1 double dash, x2 double dash, and x3 double dash are coming in the ratio of 1 raised to 2.94 raised to 3.76. Whereas we started the trial by assuming x1 dash as 1, 2.3 and 2.7. Now still they are not matching. Still they are not matching. So we'll have to go with the next trial, that is third trial. So in third trial, the initial value of assumed deflections would be 1, 2.94 and 3.6. So we start with 1, 2.94 and 3.76. We calculate the new values of inertial forces. These are F1 double dash, F2 double dash, sorry here double dash is missing, and F3 double dash. Now, based on these deflections, we calculate the new values in the same way done previously. We calculate, I am writing here the direct values. So x1 triple dash and x2 triple dash and x3 triple dash, which comes in the ratio of 1 raised to 3.12 raised to 3.95. So the assumed value was 1 raised to 2.94 raised to 3.76. Here it comes 1 raised to 3.12 and 3.95. Still it is not matching. So we'll have to start with the next trial, fourth trial, with an assumed value of deflection as this one. So we repeat the same procedure and come out with the new deflection values as 1 raised to 3.16 raised to 3.99. Now this match this with the assumed values, that is 1, 1, this is 3.12, this is 3.16, and third value of deflection is 3.95 and 3.95. So they are approximately matching. It means that in this trial, the assumed deflection values and the new deflection values are matching. So what we need to do is that we need to now equate this, that is x1 triple 4 dash value, with this value of x1 triple dash. So equating x1 triple dash value, that is 1, equal to x1 4 dash value, that is equal to this, we would be able to calculate the value of omega. Okay, so omega comes out to be 0.46 root k by m. And this natural frequency is the lowest natural frequency for this 3-degree vibration system. So over a period of number of trials, you get to know or you calculate the fundamental natural frequency of the system. I hope that this method is clear to you. So in the summary, I would say that we have dealt with various numerical methods to determine the first natural frequency of multi-degree freedom system. And what are those methods? We have dealt with Rayleigh's method, Dunkerley's method, and the last one we have discussed is the STODOLA'S method. Okay, friends, so bye for now. I recommend that you write me through email and give your feedback that whether you have got this or whether I need to improve on further. And you can also write me on my email ID, that is naveen.kumar@spsu.ac.in, about the doubts. I would try to solve your doubts in the best possible manner. Thank you very much.